Lactic acid is a naturally occurring chemical which can be synthesized from ethanol, as shown in the steps below. Draw the structure of the compound E. All right, let's start off with this one then, so we can see there's my ethanol compound there. Synthesize it into this intermediate, which will become a carboxylic acid with an OH group on there. Now, whenever you're reacting with a chemical that contains a cyanide ion, the idea here is you're going to make a nitrile because you want to make your carbon chain longer. And you can see I've got 2 carbons here. I'm becoming 3 carbons in my lactic acid. So the carbon here is going to be adding on to the chain to produce the 3 carbons in my final product. So compound E, therefore, has got to be a nitrile. And because it's coming from an aldehyde, it's going to be a hydroxynitrile. And that's why the OH there is coming from. So on your synthesis routes that I gave you, you'll notice that to turn an aldehyde into a hydroxynitrile, it actually uses NaCN and hydrogen ions. HCN is doing exactly the same job. Okay, it can be used. It's a bit more dangerous than using NaCN, and that's why it's not tend to be used as often. So this is the same reaction. So your compound here is going to be CH3 there. That CH3 is that one. The C double bond O will become an OH, which is what's on there. The H stays where it is, and we get the CN there. And you can show the triple bond between the carbon and the nitrogen, doesn't matter. There's your answer for that one. Part 2, suggest a reagent that could be used for step 2. Well, in step 2, you can see we are going to be taking our hydroxynitrile and changing it into a carboxylic acid. The OH isn't changing, the CH3 isn't changing, the hydrogen isn't changing, but the nitrile section is becoming a carboxylic acid. Now, even though this is a hydroxynitrile, it's just the nitrile that's going to react. Now, on your synthesis route, you'll notice there's no path from hydroxynitrile to carboxylic acid, but there is for nitrile to carboxylic acid. And to do that, you need to use a dilute acid. I can't get my words out. A dilute acid. So dilute hydrogen ions, you could specify. Dilute sulfuric acid, dilute hydrochloric acid. You could say acid and water. You could say H plus and water. You could say H plus aqueous. Anything that's indicating it's dilute. Because concentrated acids would not produce the carboxylic acid. Part 3, bond angles, everyone's favourite from year 1. You've got a 2-dimensional diagram. It's been drawn in displayed formula. So you've got to imagine it in 3D and remember your bond angles, your bonding pairs, your lone pairs, etc. from year 1 on your shapes. Okay, so for bond angle A, you can see around the carbon, we've got 1, 2, 3, 4 bonding pairs. Carbon can only make 4 bonds. There's going to be no lone pairs there. 4 bonding pairs. 4 bonding pairs means tetrahedral. Tetrahedral means 109.5 degrees. Bond angle B is on the oxygen here. Oxygen would have 2 lone pairs. It's forming 2 bonding pairs. It will have 2 lone pairs because it's got 6 outer shell. So 2 lone pairs, 2 bonding pairs means non-linear. Therefore, bond angle B would be 104.5 degrees, and bond angle C is here. So around the carbon, there's 3 bonding areas, 3 bonding regions coming off the carbon. So you wouldn't treat the double bond O, or the double bond, as 2 separate bonds when it comes to determining a shape and a bond angle. This is just as what is one area of bonding. So 1, 2, 3 bonding regions equals trigonal planar. So bond angle C is 120 degrees.